Welcome to the Deep Dive, where we unpack complex ideas and surface with the most important insights for you. Today, we're kicking things off with a pretty profound thought from Gottfried Leibniz. La nature ne fait jamais des sauts.
Nature never makes jumps.
Exactly. It suggests this fundamental continuity, right? Everything flows smoothly. But what if, when we're trying to figure out cause and effect, we could actually find a jump? Or maybe even, strategically use one?
That's precisely the fascinating idea we're digging into today. We're doing a deep dive into regression discontinuity designs, or RDDs.
RDDs. Okay.
Yeah, it's a really clever and pretty powerful method in causal inference, especially when you're dealing with real-world data, situations where you just can't run a perfect randomized experiment.
Right, like it's not feasible or maybe not even ethical sometimes.
Exactly. It's for those times when you're trying to nail down, what caused what, but you've got all these other factors floating around, confounding things, and you maybe can't even measure them all.
So the core idea, the whole foundation, it hinges on some kind of running variable, like a score, and a really sharp cutoff point.
Precisely. Think about it in real terms. A scholarship, maybe, that you only get if your grade average hits, say, 85%, not 84.9.
Okay, clear line.
Or specific medical treatment that a doctor prescribes, but only if some biomarker is above a certain level. Or think about social benefits kicking in, only if your income drops below a specific threshold. It's a definite, undeniable line.
Right, and here's the bit that makes you go, aha, right?
Yep.
The sort of statistical magic.
This is it. Imagine people or households or whatever units you're studying who are just fractionally above that cutoff line, and then others who are just fractionally below it.
Okay, super close.
Super close. So close that, for all practical purposes, they're basically comparable. They're alike in almost every way, except for the fact that one group just crossed the line and got the treatment, and the other just missed out.
So it's almost like random chance decided who was just over and who was just under, a kind of natural experiment.
Kinda, yeah. That's the intuition. Random luck just nudged them slightly, one way or the other, right around that critical point.
Okay. So our mission for this deep dive, then, is to unpack this basic RDD idea, figure out how it actually identifies these causal effects so well, and then, this sounds really interesting, explore how modern machine learning can, supercharge RDDs.
That's the plan.
Yeah.
Especially when you've got lots of other information, tons of data points about these individuals, what we call covariates, combining RDD's logic with ML's power over data. That's where things get really exciting.
All right, let's jump in. So let's start with the basics. You mentioned sharp RDD. What exactly does that mean, that deterministic assignment?
Absolutely. So in a sharp RDD, the treatment, usually it's binary. You get it or you don't. It's assigned with total certainty based on that running variable.
No ambiguity.
None. If your running variable, let's call it X, is greater than or equal to the cutoff, C, you get the treatment, period. If X is less than C, you absolutely do not get the treatment. It's a hard and fast rule.
Okay. And what effect are we actually trying to pin down here? Is it the effect for everybody?
Not exactly. That's a key point.
Yeah.
The main thing RDD gives you, its primary target, is the average treatment effect, the ATE, but only right at that specific cutoff value.
So very localized.
Very localized. If you want to know the effect for people way above or way below the cutoff, well, that usually requires much stronger assumptions, things that are harder to justify. You're moving away from the core strength of RDD then. Now, the identifying assumption, this is the linchpin, the thing that makes RDD work so well.
Okay, the crucial bit.
It's the assumption that the potential outcomes, what would have happened with or without the treatment, are continuous right at that cutoff point.
Meaning?
Meaning if you could magically strip away the effect of the treatment itself, there wouldn't be any other sudden jump or break in the average outcomes right at that boundary. The underlying trend flows smoothly across the cutoff.
So no other reason for a sudden difference between the group just above and the group just below other than the treatment itself.
Exactly. It's like assuming the road is smooth, and the only bump is the one caused by the treatment policy.
Got it. So if we assume that continuity holds, how do we actually see the causal effect? How do we measure that jump you mentioned?
This is the elegant part. Because we assume that underlying smoothness, any sudden sharp discontinuity, any jump we actually do observe in the average outcome right at that cutoff. Well, it has to be due to the treatment.
So Leibniz said nature doesn't make jumps.
But we might create one with a policy. And RDD lets us measure the size of that policy-induced jump, and we can confidently say that's the causal effect of the treatment right there at the threshold.
Exactly. But okay, here's a practical challenge. When we actually go to estimate this, We almost never have data for people exactly on the cutoff line, right?
They're always just a little bit to one side or the other.
Precisely. So estimation, it really boils down to figuring out what the average outcome looks like just to the left of the cutoff and what it looks like just to the right, and then measuring the difference, the gap between those 2 points. And traditionally, like before bringing in lots of extra variables, the standard way involved these local non-parametric methods. Can you unpack that a bit?
Yeah, think of it like this. Instead of trying to fit one single line or curve to all your data, you focus only on the data in a small window right around the cutoff.
Local.
Local, exactly. And non-parametric just means we're not forcing the relationship into a specific shape, like a straight line, beforehand. The most common tool is local polynomial estimation. It's basically like running a weighted regression.
Okay.
Where the observations closer to the cutoff get more weight, they matter more. You use something called a kernel function to assign those weights, like a triangular kernel gives points right at the edge of your window, less weight than points right near the cutoff. And then there's the bandwidth.
Right, the bandwidth. That defines how wide that local window is.
Yep. How much data, how far out from the cutoff you're including in that local regression.
And choosing that bandwidth sounds like it could be tricky. I bet there's a trade-off.
Oh, absolutely. It's the classic bias variance trade-off. If you make the bandwidth really narrow, focus super tightly around the cutoff, you might reduce your bias because you're really honing in on that local effect. But you're using fewer data points, so your estimate might be really noisy, have high variance. It could jump around a lot depending on your exact sample.
And if you make it wider.
Wider bandwidth gives you more data, so lower variance, a more stable estimate. But you risk introducing bias if the true relationship isn't actually a straight line, or whatever polynomial you're fitting, over that wider range. You might be smoothing over the very jump you want to find.
So finding the sweet spot is key.
Totally. And modern methods have gotten really sophisticated here. They use data-driven ways to pick optimal bandwidths and often include bias correction techniques to make sure the confidence intervals you calculate are actually reliable.
Okay, that makes sense. So RDD on its own, just with the running variable and the outcome, it works. It identifies the effect. But you mentioned a power-up. When we add covariates, those extra variables, why do that? What's the big advantage?
Right. It's not strictly necessary for identification under the core RDD assumption, but adding covariates can be hugely beneficial. There are really 4 big reasons.
Okay, lay them out.
1, efficiency and power. Just like in a randomized trial, including relevant covariates can make your estimate of the treatment effect much more precise. Tighter confidence intervals, basically. And that means you have more statistical power to actually detect an effect if one exists.
Okay, more bang for your buck data-wise.
Exactly. 2, auxiliary information. Sometimes covariates can help you deal with practical problems, like if there's some measurement error in your running variable or if you have missing outcome data for some people.
Useful.
What else? 3, treatment effect heterogeneity. This is a big one. Covariates let you explore whether the treatment effect is different for different types of people. Does the program work better for younger people or people in urban areas? Covariates unlock those kinds of questions.
So moving beyond just the average effect.
Precisely. And 4, sometimes under certain conditions, covariates might even help you extrapolate the findings. Maybe help you generalize the effect you find right at the cutoff to points a bit further away, but you have to be cautious there.
Okay, let's take a step. What if you only have a few covariates? Like a handful of demographic variables. Low dimensional, you called it. How do you use them?
The straightforward way is just to add them into that local polynomial regression we talked about earlier, usually just linearly.
Okay, seems simple enough.
Yeah, and what's really neat, mathematically speaking, is that doing this often turns out to be asymptotically equivalent, meaning essentially the same thing when you have lots of data as doing something slightly different, which is first adjusting the outcome variable based on the covariates, like predicting the outcome using the covariates and subtracting that prediction out, and then running the basic RDD on that adjusted outcome.
Interesting. So it boils down to the same thing statistically.
In many cases, yes, in the long run. And the key benefit here is usually not about bias. The bias properties often remain similar because RDD's core logic is still doing the heavy lifting. But the variance, that typically goes down.
Meaning you get a more precise estimate again?
Exactly. Sharper results, more confidence in your findings, just by including a few relevant control variables.
Right, now for the really cool part. High-dimensional covariates. What happens when you have, like, tons of potential variables? Hundreds, maybe thousands. This is where machine learning comes in, right?
This is absolutely where ML shines. One popular approach is using RDD combined with the LASSO.
Lasso, that's the one that does variable selection.
Yep. It's great at handling situations with many potential predictors. So the process is usually two steps. First, you use LASSO within a localized regression around the cutoff. Its job is to sift through all those potential covariates and select the subset that seems most important for predicting the outcome, right near that cutoff.
Like finding the needles in the haystack?
Kind of, yeah. It operates under this idea called approximate sparsity. The assumption that even if you have hundreds of variables, probably only a relatively small number of them really matter for prediction. LASSO helps you find that sparse set.
Okay, so Lasso picks the important variables, then what?
Then, in the second step, you run your RDD estimation, but you only include those variables that LASSO selected in the first step. It helps focus the adjustment on the stuff that actually matters, ignoring the noise from irrelevant variables. But you can go even further using more generic machine learning methods. This is even more flexible.
How so?
Well, instead of just making linear adjustments based on the covariates LASSO picked, you can use more powerful ML algorithms, think random forests, boosted trees, neural nets, whatever, to model potentially complex nonlinear relationships between the covariates and the outcome.
Okay, so allowing for more complicated patterns.
Exactly. The process often involves something called cross-fitting. It's a clever technique to avoid overfitting.
Cross-fitting. How does that work, roughly?
You essentially split your data into parts, or folds. You train your ML model to predict the outcome based on covariates using one part of the data, and then you use that trained model to adjust the outcomes in a different part of the data.
Ah, so the model isn't predicting on the same data it was trained on.
Precisely. It helps ensure that your ML adjustment is robust and isn't just memorizing the noise in the training data. It promotes better generalization.
Got it. So you use your fancy ML model with cross-fitting to create this adjusted outcome variable, and then
you just apply the standard RDD estimator, like the local polynomial thing we discussed, to that ML adjusted outcome.
Okay. And the amazing part is?
The amazing part is that this whole procedure is still statistically valid. It works asymptotically. And crucially, it often significantly reduces the variance of your RDD estimate, giving you more precision, even if the ML model you used for the adjustment wasn't perfectly correct.
Wow, that's powerful. So the ML helps with precision, even if it's not perfect, because the core RDD logic is still handling the causal identification from the jump.
You've got it. The ML is used for nuisance parameter estimation for the adjustment part, not for the primary causal identification step, which still relies entirely on that discontinuity at the cutoff. It's a really robust combination.
Okay, so far we've mostly focused on the overall average treatment effect at the cutoff. But you mentioned covariates also let us dig into heterogeneity. How does the effect differ for different people? That sounds super important for, like, tailoring policies.
Absolutely. The average effect is often just the starting point. Policymakers, researchers, businesses. They often want to know who is affected most, or least. Covariates are key here.
Yeah.
We can estimate the conditional average treatment effect, or CATI, right at the cutoff.
Conditional on what?
Conditional on specific characteristics, those covariates, Z. So what's the treatment effect specifically for, say, women with young children living in rural areas, as defined by your Z variables?
Okay, so much more specific effects.
Exactly. And then for a policy summary, you might calculate the average CATI. This averages those specific conditional effects across the distribution of characteristics in your population, or a relevant subgroup. It answers questions like, on average, what's the effect for women?
Right, and you mentioned something like DML helping here.
Yeah, methods related to double machine learning, or DML, can be really useful for estimating these average conditional effects robustly, especially when you want to understand how effects vary across the population based on potentially many covariates. It helps bridge the gap between the highly localized RDD estimate and broader questions about heterogeneous impacts.
This is great. Let's make it concrete. You mentioned a real-world example, the Progressa program in Mexico. How did RDD and these ML enhancements work there?
Progressa, later called Opportunidades. It's a classic, almost textbook example for RDD. It was a big anti-poverty program, a conditional cash transfer.
And the RDD setup.
Eligibility for the program, back when it started, was determined using a poverty index calculated for each household before the program began. Households below a certain threshold on this index were eligible. Those above were not.
Perfect sharp cutoff.
Exactly. A predetermined score, a clear threshold. Classic sharp RDD scenario.
And what outcomes were researchers interested in? What did they measure?
They looked at key welfare indicators, things like household consumption, both food and non-food spending. And they looked at this 1 and 2 years after the program rolled out. The data they had was pretty rich too, over 1,900 observations near the cutoff, with around 27 baseline covariates measuring household demographics, socioeconomic status, things like that.
So the million-dollar question. What did they find when they compared different ways of estimating the effect? No controls versus adding covariates linearly versus using these ML methods.
This is the really neat part, and it highlights the practical value we've been talking about. What they found was that the actual point estimates the estimated size of the program's impact on consumption were remarkably similar across all the methods.
Oh, really? So adding controls or ML didn't change the basic answer of whether the program worked?
Not fundamentally, no. The program clearly showed positive effects on consumption, regardless of the method. But, and this is the key takeaway for you, the methods that adjusted for covariates, whether just simple linear adjustment or the more complex ML methods like lasso, random forest, boosted trees, they consistently produce more precise estimates.
Meaning smaller standard errors, higher confidence intervals.
Exactly. The ML-adjusted estimates were often the most precise. So while the story about the program's impact didn't change dramatically, the confidence in that estimate, the sharpness of the finding, improved significantly when using covariates, especially with ML.
That really drives home the point. It shows the practical value. You get a clearer picture, more statistical certainty. You might detect smaller effects that you'd otherwise miss.
Precisely. Think about evaluating a policy where the effect might be modest but still important, or a business trying to optimize something where small gains matter. That extra precision can be absolutely crucial.
Okay, so let's wrap this up. Regression discontinuity designs. They're a really clever way to get at causal effects in the real world, using these sharp cutoffs almost like natural experiments.
They really are. A very credible quasi-experimental method when randomization isn't on the table. It leverages that specific discontinuity structure.
And the big story today is how combining that rigorous RDD framework with the sheer power and flexibility of modern machine learning opens up really exciting new avenues.
Absolutely. It lets us squeeze more information out of our data, leading to more precise estimates, allowing us to explore heterogeneity even in really complex settings with tons of variables. It's moving from, a basic analysis to a much more nuanced, high-resolution understanding.
It really feels like the future, this blend of econometric theory and machine learning tools.
I think so. It's enhancing our toolkit significantly.
Which leads us to a final thought for you, the listener, to chew on. We've focused today on sharp RDD, where that cutoff perfectly determines treatment. Leibniz said nature doesn't make jumps, but we found we can learn a lot when a policy does create a sharp jump.
Right. But what about situations where the jump isn't quite so, sharp? What if crossing the threshold doesn't guarantee treatment, but just makes it more likely?
Like it increases the probability you get into the program, but it's not 100% certain either way.
Exactly. That's the world of fuzzy RDDs. The discontinuity isn't in the treatment itself, but in the probability of receiving treatment. How can we still learn from those fuzzier jumps? It's another fascinating area where this blend of economic thinking and advanced methods is pushing the frontiers of causal inference, something to explore further.